Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 2, Lecture 5 of Dynamic Atomic Force Microscopy Methods. In the last class, we'd been talking about some of the analytical theory behind dynamic AFM methods, both for frequency modulation and for amplitude modulation. And we talked about the meaning of the virial and dissipation and how they play into the observables in both amplitude modulated and frequency modulated AFM. So what I've done in this slide is to summarize some of the key results which are applicable to tapping mode on the left column and to frequency modulation in the right-hand column. If you look at the left column, tapping mode, the key analytical results for tapping mode AFM, because that's going to be the focus of today's lecture, I want to reiterate a couple of key important findings that we came across last time. First of all, if you look at the first equation here, we derived an equation for the amplitude reduction. Now, the way to really understand that equation is the following. When you operate the microscope, you're going to choose a set point amplitude to operate it at. So you choose the amplitude reduction, you choose to operate the microscope at a set point A divided by A far of a certain value. What the probe and the controller do then is, if you look at the denominator on the right-hand side, we have the virial VTS and we have the dissipation ETS. What happens is the controller changes the Z distance in a way such that the virial and dissipation for the chosen amplitude turn out to be such that you get the amplitude reduction that is desired on the left-hand side. So you choose to operate the microscope at a certain set point. The Z controller adjusts the Z location so that the denominator on the right-hand side of equation 1 is such that the left-hand side equals the right-hand side. A second thing I wanted to emphasize is the tangent of phase, or the phase lag, actually consists of both ETS and VTS in its description. So we'll investigate today, the implications of these two, the amplitude reduction equation as well as the phase lag equation in some detail. In particular, we're going to focus on two very important themes that pretty much are the key success stories of the use of analytical theory in describing tapping mode atomic force microscopy. So the first question we want to explore is a subtle one and yet a very important one, which is the following. We want to explore the fact that when you as a user tune in a set point ratio, an A over A far, is it possible that that equation 1 is satisfied for two different values of Z? In other words, is it possible for two different values of Z for the denominator of the right-hand side of equation 1 to be such that the equation is valid? Why this is important is because, as I mentioned to you, the controller, when you use a set point amplitude, the controller is going to move the Z to satisfy equation 1. If there happen to be two different Z locations at which that equation is satisfied, the controller doesn't know which one to go to. And remember, at the end of the day, in tapping mode AFM, it's really the Z as a function of your scanning distance that gives you the topography information. So if you have a situation where you can get the same amplitude reduction at two different Z values, that is a very unstable situation. The controller is going to not know which way to go. It might image at a certain Z height at a certain part of the sample, might switch to another part, to another Z height at another part of the sample, and so on. So it's a very fundamental question to ask, is this relationship, is there a one-to-one relationship between the Z and the amplitude reduction? Or are there conditions under which the same amplitude reduction can be achieved by two different Z's or not? To explore this question, let us set the tip sample dissipation to 0 to start with in equation 1. The amplitude reduction equation becomes what I've shown here, and you see that in the denominator you pretty much have the virial coming up. So we're asking basically the question that is it possible, as you change the Z for the virial in the denominator of this expression to have values such that the amplitude reduction is the same for two different z values. Is it possible? And, as one thinks about it, it's possible that in a certain situation, the virial, as you approach as a function of z, so let's say you're approaching the sample, you can imagine the virial goes up and somehow comes down, and you might encounter the same value of the virial at two different z values. That's, of course, possible. But a very important way by which this can actually happen, and often happens, is if there are two different z values, one at which the virial is positive and another z value where the virial is negative. Now, if at two different z locations I find that the value of the virial is basically the same magnitude but opposite in sign, if you look at the expression for set point ratio, you notice in the denominator we have the squared of the virial. So the amplitude reduction doesn't really care if the virial is negative or positive. As long as the magnitude of it is such that the right-hand side is equal to the left-hand side, the controller is happy. So a very common way by which you can actually get two values of z, which give you the same value of amplitude reduction, is if at those two values of z, the virials have the same magnitude but opposite signs. So let's take a look at how this might actually happen. So I'm going to take you back to the equation we derived some lectures ago when we were trying to explain the physical meaning of what the virial is. And in that lecture, we talked about the fact that the virial can be regarded as some sort of a weighted area, or it can be regarded as the energy stored a measure of the energy stored in the conservative tip-sample interactions. In particular, the virial had in it an integral quantity, and that integral quantity could be regarded as some sort of a weighted average of the gradients felt by the tip during in the range of oscillation. So that expression for the integral is shown there, and if you look at the kernel of the integral, or what's inside the integrand, you find KTS, which is the tip sample gradient. Negative gradient means attractive, positive gradient means repulsive, times this weighting function 1 minus q over a the whole squared, which will weight the center location more than the extreme locations of the oscillation. So the way to think about this integrand is, if you were to plot KTS as a function of d, you would be looking at the area under the curve of the gradient versus d graph and weighting it by this weight function. Now, let us look at the figure on the left, which shows a situation where the cantilever is located at a distance z1, far from the sample. It's oscillating with an amplitude of a, back and forth. And as it's oscillating, it's basically encountering negative force gradients in the entire oscillation cycle. So if you were to look at the area under the curve here, the shaded gray area, and then, of course, you'd have to weight it by this function, you would find that integrand in the case on the left is actually negative, which would correspond to the fact that on an average, the tip is experiencing negative attractive force gradients in the range of its oscillation motion. The negative value of the integrand would correspond to a positive value of the virial because of that extra negative sign that appears on the equation on the very top. On the right-hand side, I'm going to show another case which can, in principle, have the same magnitude of virial, but a different sign. So in this case, the Z2, or the Z value, is much closer to the sample. It's still oscillating with the same amplitude, but now the tip is actually going well into the repulsive regime. And if one looks at the area under the KTS versus D graph, it has a very large positive area, and then you have to subtract a bit of the negative area. So that the overall area under the curve could actually be positive, and one could choose a value of Z2 such that the area is exactly negative of the area in the case on the left. As a result, you can easily have a situation where closer to the sample, when Z2 is brought a little closer, that you actually encounter a value of the virial which is the same in magnitude as the case on the left, but opposite in sign. So if the area becomes positive under the KTS versus D graph, then the negative sign in the virial description as shown at the top will ensure that in case 2, shown on the right, the virial is actually negative. It has the same magnitude as the one on the left-hand side, but it's a different sign. So this brings us to the definition of different oscillation states in tapping mode AFM. Whenever we have an oscillation state like the one shown on the left, the virial is going to be positive, and we call that an attractive regime of oscillation. In the case where we are in a situation on the right, we're talking about a repulsive regime of oscillation, and the virial becomes negative. Now, this is all well and good, but the question is, in practice, how would you know that your microscope is operating in the attractive or the repulsive regime? And to answer that question, we go to the second equation that we started off with at the start of this class, which is the equation for the tangent of phase. If you look at the numerator of this equation, you find that the ETS term, that is the energy dissipated into the sample, that's going to remain positive regardless of how you come in or what amplitudes you choose, because there's always going to be a net energy dissipation into the sample. So the numerator typically doesn't change its sign. The denominator, on the other hand, we have just learned, it can switch signs. In particular, when you're in the attractive regime, we define the attractive regime as one where VTS, the virial, is positive. If the virial is positive, then the tangent of phi is actually going to be negative based on this equation, because the numerator is positive. When the tangent of phi becomes negative, if you look on the sketch on the top right, I've sketched out tangent of phi as a function of phi. In order for tangent of phi to be negative, phi in fact needs to be larger than 90 degrees. So this brings us to one important result, that you recognize the attractive regime of imaging in tapping mode AFM whenever the phase lag is greater than 90 degrees. On the other hand, if you look at this equation and look at a virial value which is negative, if the virial value is negative, the tangent of phi is going to be positive, and then the phi must actually be less than 90 degrees in this case. So this brings us to the second important result. We can recognize the repulsive regime of imaging by the fact that the phase lag becomes less than 90 degrees. We're going to use these definitions a lot in coming classes, especially in week 3. So we talked about the fact that it is possible, in fact, for us to have situations where two different z values give us the same magnitude of the virial but opposite signs of the virial. And the question is, does this happen all the time, or under what conditions does this happen? Because that simple analysis that I presented to you earlier was for the case where the tip sample dissipation was actually 0. In reality, when one looks at experimental data, one finds that it's not always that one has the simultaneous possibility of having two solutions giving you the same amplitude, but with opposite signs of virials. Typically what happens in experimental situations is there are ranges of amplitudes, there are ranges of z values, operating conditions, cantilever properties, tip sample properties, under which that becomes possible. And so this leads us to one of the early key successes in analytic theory, trying to explain many aspects of how the atomic force microscope works in practice. What is shown on the top left is results from the literature from the group of Ricardo Garcia, where the amplitude is shown to decrease as you approach the sample. There's a jump which they use to identify that you have jumped from the attractive to the repulsive regime of oscillation. But what's interesting about this is they were trying to image a sample here using 3 different set point amplitudes. The largest set point amplitude, corresponding to the highest dotted or dashed line in the amplitude versus z curve, corresponds to a purely attractive state. When the microscope is operated at that set point amplitude, we are able to recover the correct image of the sample, the topography of the sample. When it chooses to operate the microscope at the lowest set point amplitude shown here, one is in the repulsive regime through the sample, and one is able to faithfully reproduce the topography of the sample. However, when one chooses to operate the microscope at the intermediate set point amplitude, you can see that at that intermediate value of amplitude, there are two different Z locations that give you the same amplitude. One is attractive, one is repulsive regime of oscillation. As a result, while choosing to scan at that amplitude, one finds that as you go over different bumps, the microscope might switch from attractive to repulsive regime, causing changes in topography that are not really related to true topography of the sample, but are just because the base of the cantilever, the Z, is changing from between those two values that allow it to retain the same oscillation amplitude. Another important consequence of the existence of attractive and repulsive states of oscillation is that depending on what you're trying to do, you may be interested in either operating the microscope in the purely attractive regime, where it experiences net attractive force gradients, or in other words, a positive virial, or you could choose to operate the microscope in a region where you get a negative virial or net repulsive force gradients. The consequences of both of these are interesting. If you're interested in imaging very soft and fragile samples, you may want to operate in the attractive regime so as to minimize the interaction forces. So this is displayed again in prior work where an antibody is being imaged under ambient conditions, and we find that when one chooses to operate at the higher set point amplitude, and so that the microscope is operating in the attractive regime, the topography is faithfully reproduced. However, when one chooses to operate in the repulsive regime, the tip sample interaction forces are so high that they crush the sample and the true topography is not recovered. And when one switches back to operating the microscope in the attractive regime, as shown in the bottom right, we're unable to recover the original topography of the sample. So in other words, what this nice example demonstrates is that for soft biological samples, when one is trying to image the sample in the repulsive regime, one might actually inflict irreversible damage on the sample. There are other examples which we'll consider shortly where one does want to operate in the repulsive regime. Typically, when one is looking at phase contrast in polymers, the repulsive regime imaging is very often intentionally used. Now, we're going to discuss this at length when we do simulations in week 3 of the class, but just as a preview, one can really change the operating conditions of the microscope to make it more likely to operate in the attractive regime or in the repulsive regime. And those conditions, broadly speaking, are the following: that if one uses soft cantilevers and small amplitudes, one tends to operate for the most part in the attractive regime. When one chooses stiffer cantilevers with large amplitudes, one typically tends to transition to intermittent tapping or repulsive regime imaging pretty soon. Of course, between these two extremes, there are many ranges or shades of gray, and all kinds of intermittent situations can arise between these two extremes. So we're now, after talking about the coexistence of attractive and repulsive regimes, we're going to talk a little bit about phase contrast in tapping mode atomic force microscopy. Now, I'm going to repeat on the left some of the key equations we derived last time. There are two important equations, equation 5 and equation 6, which relate the sine of the phase lag and the cosine of the phase lag with the energy dissipated and the virial of the tip. And the last equation is the amplitude reduction equation. Now, there are two important things I wish to highlight here. When you look at the amplitude reduction equation, it's very clear that when you as an operator or a user of the instrument choose a set point ratio, you're effectively making VTS and ETS depend on each other. They're related to each other through the last equation. In other words, if I know the amplitude reduction of the microscope and I know the dissipation, then I actually know what the virial is. And this is captured by equations 5 and 6, because if you know what the energy dissipation is, you know sine of phi. If you know sine of phi, you know what cosine of phi is, because it's just square root 1 minus sine squared phi. You don't need a separate equation 6 to tell you what cosine of phi is going to be. So this right away tells you that operating in the tapping mode, the energy dissipation and virial are not independent quantities. They're going to be related to each other. The second thing is that if one looks at equation 5 and 6 and considers a situation where the energy dissipation on the sample is 0. If the energy dissipation on the sample is identically 0, then the sign of the phase is simply going to be A over A far. It's a great result. The sign of the phase is simply going to be equal to the amplitude reduction. The cosine of the phase is whatever it needs to be in order to have the sign of phase be equal to A over A far. What it also means is that if there's no dissipation over the sample, let's say from point to point of the sample, there are certain conservative interaction properties that are changing, so the elastic modulus changes over parts of the sample. If there are no tip sample dissipation present anywhere on the sample, then what this result tells us is that the phase is going to be fixed by the set point ratio equal to A over A far, and there will be no phase contrast. In reality, of course, even in the attractive regime of operation, there is phase contrast, and associated with every material property change is always a change in dissipative properties. So it's very hard to have materials where for example, the Young's modulus is different, but the dissipative properties are the same. That's very rare to encounter. So in reality, what ends up happening is there's always going to be, even in the attractive regime, as you scan over a sample, some slight change in dissipative properties as you go from part to part in the sample, which may result in phase contrast as well. Now, to understand the meaning of phase contrast, I'm going to now go to the board and look a little more carefully at the meaning of the first equation shown on the right, which is how the sign of phase is related to energy dissipation. So what I have sketched out here is the sign of phase as a function of phase going from 0 to pi. And let us first look at the situation when the tip sample energy dissipation is 0. If the tip sample energy dissipation is 0, the sign of phase is going to be equal to the set point ratio. So let us choose this to be the set point ratio. The intersection of this line with the sign line is going to give us the two values of phase that you might get under these operating conditions. Let's call this 1 and let's call this 2. So this already tells us that even when energy dissipation is 0, there are actually two values of phase that would give you the same amplitude reduction. One value of phase corresponds to a phase less than 90 degrees, and that will correspond to a repulsive regime of imaging, where the variable is negative. The second intersection point, labeled number 2, is obviously going to be at a phase larger than 90 degrees or larger than pi over 2, which means that that's going to be the attractive regime of imaging. So any intersection of this horizontal line with the sign phase that lies on the right-hand side will be attractive regime. Anything on the left-hand side will be repulsive regime. Now, let's go ahead and then add dissipation to this into the mix. So if I add dissipation to the mix, then sign of phase is going to be equal to the following horizontal line. This horizontal line now has a height equal to A over A far times ETS. Remember, ETS is positive. As a result, this particular line has to be higher than just A over A far, because this is a positive number. It's going to raise this bar a little higher. So now, in the presence of tip sample energy dissipation, the intersection points move to 3 and 4. What's interesting here is the following, that if you're in the repulsive regime of imaging, this is repulsive, and this is attractive. If one is in the repulsive regime of imaging throughout the sample, when the energy dissipation increases, the phase lag must increase from its original value. However, when you're in the attractive regime, and you're imaging the sample in the attractive regime, increased phase lag is going to lead to a lower value of phase lag. So in this case, the phase lag decreases due to energy dissipation. In this case, the phase lag increases due to energy dissipation. So this leads us to a couple of very important conclusions. The first is, when you take an entire image in the repulsive regime, and you would know that you're in the repulsive regime in the entire image if the phase lag on the entire image is actually negative, below 90 degrees. In that case, brighter phase lag would correspond to larger energy dissipation. And because the energy dissipation and virial are related, more energy dissipation would be accompanied by lesser virial. Secondly, when the entire image is taken in the attractive regime of operation, then the situation reverses. Brighter phase lag actually corresponds to lower dissipation and more virial. And in each case, as you scan over the sample with changing dissipation amounts, the Z controller would keep going up and down to change the virial accordingly, so that the sum of the virial and dissipation are such that the amplitude reduction equation is satisfied. Now, this is great. This tells us about what the intuitive relationship between tip sample dissipation and phase contrast is going to be, but it's important also to think a little bit about physically what is happening here. A physical result or implications of what we just discussed can be summarized in this particular slide. In situations where most of the dissipation is happening in the repulsive regime due to viscoelasticity, for example, in that case, greater phase lag or brighter phase lag is going to be due to more dissipation in softer materials. In case you're doing repulsive regime imaging and the main source of dissipation is from capillary interactions, in that case, brighter phase lag would come from more capillary dissipation or more hydrophilic surfaces. On the other hand, when you take surfaces with water and image them in the attractive regime, as we'll see shortly, you have a different conclusion. If you're imaging in the attractive regime, you can also get some interesting contrast due to the presence of capillary interactions, and we'll study that very soon. And of course, this understanding also becomes a little complicated when you go to situations where dry adhesion is present and so on. And in liquids, as we'll learn later in the class, we often have very different interpretations of what we're looking at. So I want to just highlight two particular examples from the literature. The first is work out of Maganov and his collaborators. And what is the sample here is a polymer that's been rubbed on top of a silicon surface. And on the left is shown the topography images, and the right is phase contrast images as a function of different set points. The brighter phase contrast corresponds to a set point amplitude of between 50 and 60% when the tip is in the repulsive regime of operation. Now, in this particular problem, under the imaging conditions, the main source of dissipation is going to be viscoelasticity in the polymer. The silicon is expected to show very little tip sample dissipation. When you look at the phase contrast images, the first thing you need to ask is this phase lead or phase lag? Remember, because phase lead is opposite to phase lag, so all these conclusions about what's brighter, what's darker flip depending on whether phase lag or lead is plotted. We discussed this a few lectures ago. In this particular paper, they actually provided the tuning curves as shown here, where the amplitude and phase are plotted. By looking at the phase that's plotted, you can tell that the phase actually decreases as you increase the frequency, which implies that what's really being plotted is the phase lead, not the phase lag. As a result, when you look at the phase lead images, if you were to invert them into phase lag images, you would find that phase lag on the polymer patches is actually larger than on the silicon, implying that they're more viscoelastic and softer compared to silicon. So that makes sense. Here's another example where these images are of water forming on mica, and this paper has some very interesting results on water formation on graphite and so on. But what you see on the bottom row of images, for example, on the left-hand side is the layer of water sitting on mica, and the right-hand side is a phase image. In this particular case, the entire image has been taken in the attractive regime of operation, and what's being plotted is, in fact, the phase lag. In this particular case, what's interesting is the water layer appeared darker in phase lag compared to the silicon surrounding mica. The situation is kind of resolved by really looking into the fact that the image is taken in the attractive regime. In the attractive regime, remember, less phase lag corresponds to greater energy dissipation. We do expect, as the tip is going over the water surface, that the capillary neck forms and breaks, leading to larger energy dissipation. So with that, I'd like to conclude, and we'll continue in the next lecture on talking about average and peak forces in AFM. Thank you.